Every second, deep inside your body, countless quantum events unfold. Electrons shift, particles interact, and occasionally, an unstable atom decays. According to everything we've ever measured, the exact moment that decay occurs is not determined by any hidden clock or invisible force. It is fundamentally unpredictable. That idea should be impossible. Every effect is supposed to have a cause. Yet quantum mechanics, the most accurate scientific theory ever developed, appears to place probability at the very foundation of reality. But there is an even stranger possibility. What if those probabilities never truly collapse? What if every possible outcome actually continues to exist? In 1957, a young physicist named Hugh Everett proposed exactly that. He wasn't trying to invent science fiction. He simply refused to add anything to the mathematics that wasn't already there. His interpretation was dismissed by many of his contemporaries, and Everett eventually left academic physics. Decades later, however, his idea, the many worlds interpretation, has become one of the most discussed ways of understanding quantum mechanics, even though no interpretation has yet been experimentally confirmed over the others. If Everett's picture of reality is correct, then every quantum event creates a branching universe where every possible outcome exists. Follow that idea to its logical conclusion, and it leads somewhere deeply unsettling. Through radioactive decay, impossible coincidences, black holes, and the distant future of the cosmos, it arrives at a thought experiment so disturbing that many physicists refuse to take it literally. A universe in which, from your own point of view, death may never be experienced. This idea is known as quantum immortality. Whether it reveals something profound about reality or simply exposes the limits of one interpretation of quantum mechanics is the mystery we're about to explore. Imagine you could watch a death the way a physicist would. Not with grief, not with meaning, with instruments. Every detector science has ever built arranged around a living body. Scales sensitive enough to register a single grain of dust. Thermometers tracking thousandths of a degree. Sensors for every known field, every known particle. And then you wait for the moment life ends. Here is what your instruments record at that moment. Almost nothing. No measurable mass is lost. Nothing detectable leaves the body. The warmth simply begins, very slowly, to leak into the room, exactly the way a cup of tea cools. And this is not a failure of our technology. Every law of physics agrees on one astonishing fact. At the moment you die, the universe doesn't lose a single atom. Not one. It doesn't lose a single joule of energy. Not one. These are the conservation laws, the deepest rules science has ever found, tested for centuries, in every laboratory on Earth. From colliding particles to colliding galaxies. No verified exception. Ever. From the perspective of conserved quantities, death subtracts nothing measurable from the universe. Which raises a disturbing question. If nothing physically disappears, what exactly died? Hold that question, because the answer is stranger than you think. And it's the first clue in the mystery we came here to solve. Start with your atoms. The iron in your blood was forged inside a massive star that exploded billions of years before the sun existed. The calcium in your bones, the oxygen in your lungs, the carbon in every cell. All of it was built in stellar furnaces and scattered across space when those stars died. You've probably heard this before. We are star stuff. But almost everyone misses what it actually implies. Every atom you own is billions of years old. Every atom you own will outlive you by billions more. The universe has been recycling this material forever. You are not the first owner of your matter. And here's the part nobody tells you. You're not even the current owner. Not really. The child you once were no longer exists. Not physically. Almost every atom that formed that child's body has already left. Exhaled. Shed. Washed away year after year while you weren't paying attention. Those atoms have become air, water, trees, perhaps another person. The body in your oldest photographs, the one you remember being, has been dismantled and shipped back into the world, almost in its entirety. What you're living in right now is a replacement, rebuilt from food and water and air over and over your whole life. If losing your atoms were death, you have already died many times. And yet, somehow, you never felt yourself disappear. Something survived every one of those replacements. Something that isn't any particular atom because the atoms keep leaving. So what is it? Watch a whirlpool in a river. The water passing through it is never the same water from one second to the next. The river flows straight through, but the whirlpool remains. The same shape, the same spin, the same structure for hours. The whirlpool is not made of water. It is made of a pattern that water temporarily takes. You are not made of atoms. You are a pattern that matter temporarily takes. 10 trillion particles arranged in one extraordinarily specific way. The sequence of your DNA. The wiring of 86 billion neurons. The connections that store every memory you have. In physical terms, all of it is one thing. Information. Not the stuff, the arrangement of the stuff. And this is where our original question returns. Because if you are not your atoms, if you are a pattern written in atoms, then the question, can you survive death, quietly transforms into a very different question. Could that pattern ever continue somewhere else? Don't answer yet. Physics has something to say first, about how patterns end. Right now, your body is fighting a war you never notice. Every second, your cells repair damage, correct errors, rebuild what's breaking down. This maintenance never stops, and it isn't optional. It runs on a constant stream of energy, and every joule of it is spent holding your pattern together against the most patient force in the universe. Entropy, the second law of thermodynamics. Left alone, order decays. Structures crumble. Information degrades into noise. Nothing escapes this law. Not stars, not planets, not you. Life doesn't break the rule. Life bribes it. An organism keeps its own small region ordered by exporting disorder into its surroundings, the way a refrigerator keeps its inside cold by heating the room behind it. A living body is a temporary rebellion against entropy, funded by a lifetime of stolen energy. And now, finally, we can say what death actually is. Not emotionally, physically. Death is the moment the maintenance stops. The matter, untouched. The energy, dispersed but conserved. What ends is the upkeep. The pattern stops paying its energy bill, stops correcting its errors, and entropy, no longer resisted, begins to reclaim the structure. Atom by atom, the arrangement blurs back into the background of the world. The whirlpool flattens. The river flows on. That sounds final. It might not be, because look at what just happened to the oldest question humans have ever asked. For all of history, does anything survive death meant asking whether some invisible substance, a soul, escapes the body. Science can't measure that. Science has nothing to say. But we just saw that what ends at death is not a substance at all. It's a pattern. Information. And about information, physics has a great deal to say. So here is the question, stripped of all mysticism. The question this entire documentary hangs on. Can a pattern be permanently erased from the universe? Your intuition says yes. Obviously. Burn a letter, the words are gone. Shatter a sculpture, the form is destroyed. But be careful. Your intuition also said matter disappears when a body decays. And we just proved it doesn't. It only disperses. The universe is a far more careful bookkeeper than everyday experience suggests. In fact, whether information can ever truly disappear has become one of the deepest open questions in theoretical physics. When physicists pushed it to the extreme, asking whether even a black hole can delete information, it ignited a scientific war that lasted decades, involved the most famous physicist in the world, and ended with him publicly admitting he was wrong. We'll fight that war later in this story, because there's a problem we have to face first. A problem sitting underneath everything we've said so far. Everything in this episode has assumed one simple idea, that every event has one outcome. An atom decays, or it doesn't. A neuron fires, or it doesn't. A person lives, or dies. It seems beyond question. It's the logic reality itself appears to run on. But your pattern is written in particles, and particles do not follow the reliable clockwork rules of the everyday world. They follow quantum mechanics, the most precisely tested theory in the history of science. And quantum mechanics refuses to make that promise. At the deepest level of reality, nature may never choose a single future. The equations don't describe one outcome happening. They describe all of them, unfolding together, perfectly, mathematically, with nothing in the physics that ever selects a winner. For nearly a century, physicists have argued about what that means. Most chose to look away. One of them didn't. And if he was right, then death itself may look very different than we imagine. Somewhere in the room you're sitting in right now, there is almost certainly a single unstable atom. Perhaps it's a trace of radioactive potassium in a banana on your kitchen counter, or a carbon-14 atom sitting quietly in the wood of your desk. At some point, maybe in the next second, maybe in 10,000 years, that atom will decay. It will spit out a particle, transform into something new, and release a tiny burst of energy. And here is the uncomfortable truth we established at the very beginning of this story. No force, no law, no hidden mechanism anywhere in the known universe determines when. Quantum mechanics can calculate the odds with breathtaking precision. It cannot, even in principle, tell you the moment. Now ask what should be a simple question. In the instant before we check on that atom, before any measurement is made, has it decayed or hasn't it? Common sense insists it must be one or the other. The atom is out there, real and physical, and reality doesn't wait for us to look. But when physicists write down the actual mathematics describing that atom, something deeply strange appears. The equation, the Schrödinger equation, the beating heart of all quantum theory, does not describe an atom that has decayed, nor an atom that hasn't. It describes both conditions at once, evolving together, side by side, each as real as the other in the mathematics, flowing forward in time in perfect, superposed silence. The equation simply refuses to choose. For the founders of quantum mechanics, gathered around Niels Bohr in Copenhagen in the 1920s, this was intolerable. Their solution became the official doctrine of physics for nearly a century. And it goes like this. The mathematics describes possibilities, and the moment a measurement occurs, one possibility abruptly becomes real, while all the others vanish. They called it the collapse of the wave function. Ask when exactly this collapse happens, or what physically causes it, or why a measuring device gets to do something no other object in the universe can do, and the Copenhagen answer was essentially, don't ask. Calculate, predict, publish. The theory works magnificently, but do not inquire too closely into what is actually happening. And here is the detail that should bother you. The detail that bothered a young graduate student at Princeton enough to stake his career on it. The collapse appears nowhere in the mathematics. Nothing in the Schrödinger equation ever collapses. The equation describes possibilities multiplying, spreading, entangling with everything they touch, smoothly, deterministically, forever. Collapse was not discovered in the physics. It was bolted on afterward, by hand, because the alternative seemed too absurd to say out loud. That graduate student was Hugh Everett, and in 1957 he said it out loud. His argument had a kind of ruthless simplicity that still divides physicists today. The Schrödinger equation is the most successful equation in the history of science. Suppose we simply believe it. All of it. With nothing added and nothing subtracted. If the mathematics says the atom exists in two conditions at once, then it does. And if a detector measures that atom, the mathematics is equally clear about what happens next. The detector doesn't force a choice, it joins the superposition. Now it's the detector that exists in two conditions, one that registered a decay, one that didn't. And if a physicist reads that detector, the same logic climbs another rung. The physicist joins the superposition too. There is now a version of her who saw the atom decay and a version who saw nothing. Both written into the same universal mathematics, both experiencing their result as the only result, each entirely unaware that the other exists. Nothing collapsed. Nothing vanished. Reality didn't choose. It divided, or more precisely, it revealed that it had been quietly capable of dividing all along. This is the many worlds interpretation, and it's worth pausing on what it is not. It is not an exotic add-on to quantum mechanics, not a speculative extra dimension, not science fiction bolted onto science. It is what you get when you remove an assumption, when you take the one equation everyone already trusts and refuse to interrupt it. The many worlds were in the mathematics the entire time. Copenhagen's collapse was the invention. But wait, If reality is constantly splitting, why have you never seen it happen? Why does your coffee cup sit in exactly one place? Why has no one ever caught a detector reading two results at once? This objection stalled Everett's idea for decades, and the answer, worked out carefully by physicists in the 1970s and 80s, turns out to be one of the most beautiful mechanisms in modern science. It's called decoherence, and you can see it without a single equation. Picture our unstable atom again, and imagine its two possible histories, decayed and not decayed, as two expanding ripples on the same pond, overlapping, capable of interfering with each other. As long as the atom is perfectly isolated, those ripples genuinely mix, and experiments can detect their interference. This is routine laboratory physics, confirmed thousands of times with atoms, molecules, and increasingly large objects. But nothing in the real world stays isolated. The instant the decay touches its environment, a single air molecule bounces differently, a single photon scatters off the detector's needle. The two ripples begin recording themselves into the world around them. Each history gets stamped, copied, and broadcast into billions of particles, and the two versions of events stop being able to overlap, the way two drops of ink, stirred into opposite ends of an ocean, can never find each other again. Physicists can calculate how fast this happens for an object the size of a dust grain, let alone a human being, and the timescales are so short they barely have names, far less than a trillionth of a second. This is why you never see the split. The branches don't fly off to distant galaxies, they remain right here, occupying the same space, but sealed off from one another more perfectly than any wall could manage, separated not by distance, but by information. Decoherence, it's worth being honest, doesn't prove the other branches exist. What it proves is why, if they exist, you could never see them. The interpretation remains exactly that, an interpretation, unconfirmed against its rivals. But it dissolved the strongest objection, and it's a major reason that, in modern surveys of physicists, Everett's once ridiculed idea now regularly polls as a leading contender for what quantum mechanics actually means. Now, bring this home, because this was never really about atoms. Your body, as we discovered in Part 1, is a pattern written in roughly 10 trillion particles. And those particles are not spectators to quantum events, they are participants. Every second, inside you, radioactive atoms decay. About 4,000 potassium-40 decays per second in an average adult body. Each one a genuine quantum event, each one undetermined until it happens. Every second, molecules collide, tunnel, and bind in ways that quantum uncertainty steers. If Everett is right, every one of those events is a branch point, which means the pattern that is you is not a single thread running through time. It is a tree, a structure of staggering, incomprehensible richness, versions of you splitting from versions of you, thousands of times per second, every day of your life, each branch experiencing itself as the one and only you, each carrying your memories forward into a slightly different future. The you watching this video is one twig on that tree. And here's the thought that should keep you up tonight. You have no way, even in principle, of knowing which twig you are. Every version of you feels exactly like the original. Before we begin, One thing must be said plainly. What you are about to hear is a thought experiment. No one has ever performed it. No one ever should. Its inventors were not proposing an experiment, they were building a trap for an idea, a scenario designed to force Everett's mathematics to confess what it really implies. Physicists do this all the time. Einstein imagined riding a beam of light. Schrödinger imagined a cat in a box. Nobody chased photons or poisoned cats. The imagining alone was enough to expose what a theory was hiding. But there is a difference here. Einstein's daydream revealed the nature of time. Schrödinger's revealed the absurdity of superposition. This one reveals something no other thought experiment in physics has ever dared to touch. What your own death looks like from the inside, if the inside never ends. The idea surfaced in 1987 from a robotics researcher named Hans Moravec and was later sharpened into its famous form by the physicist Max Tegmark, the same Tegmark we will meet again before this story is over. The setup is brutally simple. Take the unstable atom we have been following since the first minute of this documentary. Wire it to a detector, and wire the detector to a gun aimed at the experimenter's head. If the atom decays within the next 10 seconds, the gun fires. If it doesn't, the mechanism clicks harmlessly. The engineering is arranged so that death, if it comes, arrives faster than any nerve signal can travel, faster than pain, faster than awareness, faster than the brain can register that anything happened at all. This detail is not cruelty. It is the hinge of the entire argument, and you will see why in a moment. The odds are 50-50, a coin flip decided by the deepest randomness the universe possesses. Now the experimenter sits down, and the countdown begins. Watch first from the outside, from a chair across the room. Quantum mechanics tells you exactly what to expect, and it does not care which interpretation you believe. There is a 50% chance you watch the experimenter die in the next 10 seconds. If somehow they survive and insist on going again, the odds of surviving twice are 1 in 4. 10 rounds, 1 in 1,024. 30 rounds, roughly 1 in a billion. From the outside, this is not a mystery. It is a mortuary. Run the experiment anywhere, in any lab on Earth, and the story ends the same way, quickly, with statistical certainty. Every physicist agrees on this. Copenhagen agrees. Everett agrees. The outside view is not where the theories part ways. Now, sit in the chair. If Copenhagen is right, if each quantum event has exactly one outcome, then your prospects are precisely what the outside observer calculated. The atom decays, or it doesn't, once, and with each round you are riding a coin flip toward near certain oblivion. 10 clicks would make you a 1 in 1,000 lottery winner. 30 would make you a walking miracle. But if Everett is right, the arithmetic of experience changes in a way that has unsettled every physicist who has taken it seriously. When the countdown ends, the universe does what we watched it do in part 2. It branches. In one branch, the atom decayed, the gun fired, and a body slumps in a chair. In the other, a click. Both branches are equally real. Both are written into the same universal mathematics. But now ask the only question that matters, the question this machine was built to isolate. In which branch is there an experience of what just happened? Not which branch exists, both do. Which branch contains a point of view? The branch with the body contains no observer. Death arrived faster than perception. There is no one in that branch to notice anything, no final flash, no fading, no experience of an ending. By construction, there is nothing it is like to be in that branch at all. Every ongoing experience, every thread of memory and awareness connected to the person in the chair exists in exactly one place, the branch with the click. So from the inside, click. You check the detector. You take a breath. 10 seconds passed and the machine didn't fire. Round 2. The universe branches again, and again, the only version of you having any experience whatsoever is the one hearing click. Round 10. Click. Round 30. Click. The outside observer's 1 in a billion miracle is, from the chair, the only story that was ever experienced. Not because you were lucky, because in Everett's universe, the unlucky branches contain bodies but no witnesses, and your next moment of experience, wherever it exists, can only exist where experience continues. Let this settle, because it is the coldest piece of logic in this entire series. Nothing is protecting the experimenter. No force deflects the bullet, no guardian tips the quantum dice. In the overwhelming majority of branches weighted by the mathematics, the experimenter dies, and their family grieves, and their colleagues bury them, and that is the reality those branches contain forever. The claim is not that you cannot be killed. The claim is stranger and narrower, that dying is something that happens in other people's branches. From your own point of view, the only point of view you will ever have, there is always a next moment, because the branches without a next moment are branches without a you to notice their absence. Survivorship here is not a bias in the data, it is the filter that decides which futures get experienced at all. You can feel how seductive this is, and you should also feel suspicious. So let's be honest about what the machine does and does not establish. First, everything rests on Everett being right, and as we said plainly in Part 2, no experiment has yet crowned any interpretation of quantum mechanics. If collapse is real, the machine is just an elaborate way to die. Second, notice how much work that word instantaneous is doing. The gun kills faster than perception, cleanly separating branches with observers from branches without them. Real dangers are almost never like that, and whether this logic survives contact with the real world's slow, messy, partial ways of dying is a question we are deliberately saving for the end of this story, because it is where the whole idea faces its hardest test. And third, the strangest feature of all, the machine offers proof that can never be shared. Suppose you sat in the chair and heard 1,000 consecutive clicks. From the inside, you would hold something close to experimental evidence that Everett was right. The alternative would mean you'd won a lottery beyond all reason. But your evidence would be worthless to everyone else. In almost every branch, colleagues watched the experiment fail. The surviving you, waving a 1,000-click logbook, exists in a sliver of reality so thin that no outside observer could ever be persuaded by it. Quantum suicide is sometimes called the only experiment in physics whose results can be known, but only by the one person who can never publish it. And yet, Even if you set the machine aside as a philosopher's toy, it has already done something irreversible to our story. It has converted Everett's branching, an abstract picture of splitting detectors and duplicated physicists, into a survival machine. It revealed that in a branching universe, conscious experience doesn't sample the branches fairly. It flows, automatically and without exception, down the corridors where it can continue to exist. And that raises a question that should now be forming, uninvited, somewhere in the back of your mind. Your life is not a laboratory setup, but it is a body whose fate hangs, moment to moment, on quantum events. We counted them in part 2, thousands per second. If experience always finds the surviving branch, how far can that go? Through an illness? Through an accident? Through old age itself? Hold that question, because before we can answer it, the idea has to survive a challenge from a completely unexpected direction. Everything so far has depended on Everett's branches, on the quantum tree. But what if Everett is wrong? What if the wave function really does collapse and there is only one universe, one history, one you? Here is the twist that almost no one sees coming. It might not matter. Because while quantum physicists were arguing about branches, cosmologists, studying the birth of the universe itself with entirely different tools and entirely different mathematics, were quietly arriving at the same impossible conclusion. Other versions of you. Not in other branches, in this universe. Out there, in the dark, at distances so vast that light has never had time to cross them. And unlike Everett's branches, these copies would be made of ordinary matter, in ordinary space, just unimaginably far away. There is a wall around everything you have ever seen, and it is made of time. Look out from Earth in any direction with the most powerful telescopes ever built, and eventually you run out of universe to look at, not because the universe stops, but because light does. The cosmos is 13.8 billion years old, and light moves at a fixed speed, which means there is a horizon around us, a sphere, roughly 93 billion light-years across once you account for cosmic expansion, containing everything whose light has had time to reach us. Astronomers call it the observable universe, and every galaxy you have ever seen a picture of lives inside it. But notice what that horizon actually is. It is not a wall in space. It is a limit on seeing. The same kind of limit a ship's captain faces at sea, where the ocean visibly ends in a clean circle at the horizon, and yet no sailor has ever believed the water stops there. Here is the fact that this entire episode rests on, so hold it carefully. Nothing we have ever measured suggests the universe ends at our horizon. The best data we have, from the geometry of space itself, measured in the afterglow of the Big Bang, shows space to be flat as far as we can probe it. And flat space, if it keeps going, has no natural place to stop. The universe has never told us it ends. We simply cannot see past the edge of the light. Why does that matter for our story? Because of something you already know, something we established in the very first episode and have been carrying ever since. You are not a substance. You are a pattern, a specific arrangement of particles in a region of space, and, crucially, a finite one. There are only so many particles in the volume a human body occupies, and quantum mechanics itself guarantees that they can only be arranged in a finite, though astronomically enormous, number of distinguishable ways. The same is true, scaled up, for our entire observable universe. A region of this size, at this temperature, can hold only a finite number of possible configurations of matter. Physicists can even estimate the number. It is a 1, followed by more zeros than there are atoms on Earth. A quantity so large, the word astronomical is an insult to it. But it is not infinite. And now the trap closes. And it closes by pure counting. If space goes on forever, and again, no measurement has ever contradicted this, then it contains infinitely many regions the size of ours. Infinitely many rooms, so to speak, each furnished from the same finite catalogue of possible arrangements. An infinite hotel with a finite list of room designs must repeat its rooms. Not might, must. Somewhere out there, beyond the horizon, the arrangement of particles that constitutes you, this body, this brain, these memories, down to the last atom, occurs again. And again. Infinitely many times. This is not mysticism, and it is not Everett. Notice that we haven't used a single quantum branch. It follows from 3 ingredients only: space that continues, matter arranged by finite rules, and the merciless arithmetic of infinity. The physicist Max Tegmark, the same man who sharpened the suicide machine, called this the Level 1 multiverse, and he did something almost comically concrete with it. He estimated the distance to your nearest copy. The number is 10 to the power of 10 to the power of 28 meters, a number so vast that writing it out in full would take more digits than there are particles in our visible universe. Unreachable, unobservable, forever beyond contact. But if the assumptions hold, they are out there, as physical as you. And the assumptions themselves have a pedigree that makes them hard to dismiss, because they emerge from our best theory of how the universe began. In 1981, the physicist Alan Guth proposed that the Big Bang was ignited by inflation, a burst of expansion in the universe's first fraction of a second, so violent that space itself stretched faster than light can cross it, taking a region smaller than an atom to cosmic scales in less time than light takes to cross a proton. It sounds extravagant, but inflation earned its place the hard way. It predicted, decades in advance, the precise statistical pattern of hot and cold spots in the Big Bang's afterglow, predictions that satellites have now confirmed to stunning precision. Inflation is why the sky looks the same in every direction. It is why space measures flat. It is, currently, the leading account of our origin. But when theorists followed inflation's own equations forward, they found something they never asked for. In most versions of the theory, inflation doesn't end everywhere. It ends in patches, pockets where the stretching stops and matter condenses and stars ignite, while beyond them, space goes on inflating, forever spawning new pockets, like bubbles forming in an endless boiling ocean. Our entire universe, in this picture, is one bubble. This is eternal inflation, and it must be said honestly, unlike inflation itself, the eternal part is genuinely speculative, a prediction of equations we cannot follow past our horizon, endorsed by many cosmologists, doubted by others, testable by no experiment anyone has yet devised. But if it is right, the multiverse acquires a second level. Other bubbles, Tegmark's Level 2, may have inherited different physical constants, different particle masses, different laws. Most would be sterile. No atoms, no chemistry, no one home. But among endless bubbles, some would roll constants friendly to matter, and in those, the level 1 argument runs all over again. Infinite space, finite patterns, endless repetition. The tree of quantum branches was already dizzying. This is a forest of trees. Now put the two pictures side by side, because this is where the episode has been heading all along. From quantum mechanics, branches, versions of you generated thousands of times per second by decaying atoms, sealed off from each other by decoherence, sharing your space, but never your experience. From cosmology, copies, versions of you assembled by infinite space from the same finite catalogue of patterns, separated not by information, but by unswimmable oceans of distance. Two completely different theories. Two completely different kinds of mathematics, one from the physics of the very small, one from the physics of the very large. Neither was built with the other in mind, and neither needs the other to work. Yet both, followed honestly to their conclusions, hand us the same impossible sentence. The pattern that is you exists in more than one place. Tegmark noticed something further, and it is the kind of observation that keeps physicists arguing at conferences long after midnight. Ask what practical difference there is between a quantum branch where you survived some event and a distant level 1 region where an identical copy of you survived the identical event, and the answer, disturbingly, is that there may be none. In work with the cosmologist Anthony Aguirre, Tegmark showed the two descriptions can be made mathematically parallel. Infinite space may play the role of Everett's branches, with the universe's endless copies standing in for the quantum tree. If anything like that is right, then quantum immortality's strange logic, experience continuing wherever continuation exists, no longer depends on Everett winning the interpretation war at all. The copies don't need branches. Infinity builds them out of ordinary matter, in ordinary space. The idea we set out to test has just survived the death of its own favorite assumption. But before you feel either comforted or terrified, look at what every version of this survival actually amounts to. Branches, bubbles, copies beyond the horizon. All of it. In every single case, what survives is the same thing. The only thing it has ever been since we watched those instruments record nothing leaving a dying body. A pattern. An arrangement of matter carrying information. Every copy of you, quantum or cosmic, is that pattern written somewhere in the universe's ledger. Which means this entire story now balances on the question we raised in the first episode and deliberately walked away from: whether the ledger can be wiped. If the universe can truly destroy information, burn the pattern out of existence everywhere completely, then copies and branches merely postpone an ending that physics guarantees. But if the universe cannot destroy information, then something about you is written in permanent ink. In the 1970s, the most famous physicist alive looked into the one object in the cosmos that seemed built for perfect erasure. An object whose gravity devours light itself, and declared that information dies there. He was so confident, he bet on it. The war over that bet lasted 30 years, dragged in half of theoretical physics, and ended with the great man standing before the world's cameras, conceding. What he conceded, and what it means for the pattern that is you, is where we go next. In the first episode of this story, we asked whether a pattern can be permanently erased from the universe, and your intuition said yes, burn a letter and the words are gone. It is time to settle that. Physics agrees that the words become unreadable, ink chars, paper curls, smoke disperses. But quantum mechanics makes a far stronger claim about what happens next, and it is one of the least known and most consequential principles in all of science. Written into the mathematical foundations of quantum theory is a property called unitarity, and stripped of its formalism, it says this: the universe never forgets. The complete information describing any physical system, every particle state, every correlation, every detail, is never created and never destroyed, only transformed. Burn the letter, and in principle, the information in those words survives, encoded in the precise agitation of every smoke particle, the exact spectrum of every photon of firelight, the microscopic dance of heat in the ash. No conceivable technology could reassemble it, and none ever will. But the physics is unambiguous. The transformation is, at bottom, reversible. Nothing in the equations allows the universe to take a state and truly delete it, any more than the conservation laws we met in Part 1 allow it to delete an atom. Scrambling is permitted, encouraged even. Entropy is the universe scrambling things. Erasure is not. And this principle is not decoration. Unitarity is load-bearing. Quantum mechanics probabilities only make sense because of it. Without it, the chance of all possible outcomes would no longer add up to 100%, and the most successful theory in scientific history would collapse into nonsense. If you are a pattern, and by now, that is the one thing this series has established beyond argument, then unitarity says the universe is keeping your receipts. All of them. Forever. Unless, of course, the universe contains a shredder. And it does, or it seemed to. A black hole is what remains when a massive star's core collapses past the point of no return. An object whose gravity grows so extreme that within a boundary called the event horizon, escape would require moving faster than light. Nothing does. Whatever crosses that boundary, gas, planets, letters, people, leaves the visible universe, and general relativity adds an insult. From the outside, every black hole is featureless. Mass, spin, electric charge. Those three numbers are all a black hole reveals, regardless of whether it swallowed a star or an encyclopedia. Physicists call this the no-hair theorem, and you can already feel the tension tightening. Where did the information go? For decades, there was a refuge. Perhaps it survives inside, hidden but not destroyed, locked behind the horizon forever. Locked is not erased. Unitarity could live with locked. Then, in 1974, Stephen Hawking took that refuge away. In a calculation now considered one of the landmarks of 20th century physics, he combined quantum theory with the physics of the horizon and found something no one expected. Black holes are not perfectly black. The quantum vacuum near the horizon leaks a faint glow, Hawking radiation, and that leak carries energy away. Slowly, over timescales that dwarf the current age of the universe, a black hole evaporates. It shrinks, glows hotter, and finally vanishes entirely. Now the trap has no exit. If the black hole is gone, the information is locked inside is no longer an answer. There is no inside. And Hawking's own mathematics said the escaping radiation was featureless, thermal, carrying no imprint whatsoever of what had fallen in. His conclusion was as blunt as a slammed door. The information is destroyed. Not scrambled, gone. The universe, he claimed, forgets after all. Understand what was actually at stake, because this was never really about black holes. If information can die in a black hole, then unitarity is not a law. It is a habit the universe breaks when pressed. The foundation cracks. That is why Hawking's result ignited what physicists themselves called the Black Hole War, a 30-year confrontation dragging in half of theoretical physics, with Hawking leading one side and quantum theorists, most vocally Leonard Susskind and Gerard 't Hooft, refusing to surrender the foundation. In 1997, the dispute became a formal wager. Hawking and the relativist Kip Thorne bet the quantum physicist John Preskill that information swallowed by a black hole is lost forever. The stake, with the dry humor of physicists, was an encyclopedia, from which, the wording specified, information can be recovered at will. And then, over the following years, the tide turned, not through philosophy, but through calculation. Studies of black hole entropy suggested a horizon somehow keeps a record of what falls through, with a storage capacity written on its surface, a result so strange it birthed the holographic principle, the idea that everything happening inside a region of space can be fully encoded on its boundary, the way a hologram encodes 3 dimensions on a flat film. Then, in 1997, the theorist Juan Maldacena constructed a mathematical universe, simplified but complete, in which gravity on the inside is exactly equivalent to a quantum system on the boundary, a system where unitarity visibly holds and nothing can be erased. If a black hole in that universe destroys information, the equivalence breaks. It doesn't. It was not a proof about our own cosmos, but as evidence, it was devastating. In 2004, Stephen Hawking stood before the world's cameras at a conference in Dublin and did what almost no titan of any field ever does in public. He conceded. He handed Preskill the encyclopedia, a baseball encyclopedia as it happened, and acknowledged that information, in his revised view, escapes after all, smuggled out in subtle correlations within the radiation, unreadable in practice, present in principle. And the story did not end with a handshake. Beginning in 2019, a new generation of physicists completed calculations that had been impossible in Hawking's day, showing the radiation's information content rising and falling along the exact curve that unitarity demands. Honesty requires the caveat, and it matters. Quantum gravity remains unfinished. The final account of how the information escapes is still fought over, and a minority of serious physicists still dissent. The war produced a consensus, not a certainty. But the consensus is remarkable. The one object in the cosmos, purpose-built for perfect erasure, apparently cannot erase. Stop and look at how far this reaches. The question this series asked in its opening minutes, what exactly dies if nothing measurable leaves, has now been chased to the most extreme environment reality offers, and it came back with the same answer. Matter cannot be deleted. We knew that from the start. Now, if the consensus of the black hole war holds, information cannot be deleted either. The pattern that is you, the arrangement we watched survive the replacement of every atom, the pattern branching through Everett's tree thousands of times per second, the pattern repeating through infinite space beyond the horizon, that pattern is written in a medium the universe itself appears incapable of wiping. Deleting you is not merely difficult, If unitarity holds everywhere, it is unlawful, forbidden by the same architecture that makes probability itself add up. Even a black hole, given a body, must eventually hand back every bit. But now, be as honest as we have been at every step, because there is a cold current running under this warm conclusion, and you may have felt it already. Preserved is not alive. The information in the burned letter survives in smoke and ash, but the ash does not read itself. The record of a symphony pressed into scattered radiation is not music anyone hears. What unitarity guarantees is the ledger, not the reader. Your pattern persists as an entry in the universe's unerasable books, transformed past all recognition. And an entry does not experience anything. For quantum immortality, the idea we are actually testing, the ledger alone was never going to be enough. Experience, as the suicide machine taught us, continues only where there is a functioning pattern, organized, energized, computing, alive. So the real question was never only, can the entry be erased? It is also, how long can the universe keep any entry running? Because here is what we have quietly assumed through 5 episodes: branches that keep branching, space that keeps existing, energy that keeps flowing. Every survival we have described unfolds inside a universe. And the universe, it turns out, has a medical chart of its own. Its stars are already dying faster than they are being born. Its expansion is accelerating, emptying the sky. And sleeping inside the very field that gives particles their mass, there may be a quantum instability that could end everything. Not gradually, not someday, but at the speed of light, without warning, starting from a single point. The universe that cannot delete you is not certain to keep the lights on. How long can it? That is the next chapter. Every survival story we have told so far, the branches, the copies beyond the horizon, the ledger no black hole can burn, unfolds inside a container. That container is the universe itself, and we have been treating it the way healthy people treat their own bodies, as something that will simply go on. It will not. The universe has a medical chart, and physicists have been reading it with increasing precision for decades. It records 2 very different prognoses. One is a death sentence with no scheduled date, sudden, total, and, by its nature, impossible to see coming. The other is slower, gentler, and far more certain. Not an execution, but an exhaustion. If quantum immortality means experience continuing wherever continuation is physically possible, then everything now depends on a question no thought experiment can dodge. How long does the universe stay a place where continuation is physically possible? Start with the sudden death, because it is the strangest object in modern physics that almost no one outside the field has heard of. Space, as quantum theory describes it, is never truly empty. Even a perfect vacuum seethes with fields, and one of them, the Higgs field, confirmed by the discovery of its particle in 2012, permeates everything, giving fundamental particles their mass. Think of that field as a ball resting in a valley. The valley it occupies sets the rules. Particle masses, the strength of forces, the possibility of atoms. Here is the disquieting discovery. When physicists feed the measured mass of the Higgs boson and the top quark into the equations and extrapolate, the calculation suggests our valley may not be the deepest one available. There may be another valley far below, and a ball resting in a high valley is not stable. It is metastable, secure against any ordinary push, but not against quantum mechanics, because, as we have known since the first episode, quantum events do not need a cause. Through the same tunneling that lets an unstable atom decay without reason, a microscopic region of space could one day slip into the deeper valley. If that ever happens, the consequences are not local. The lower energy region becomes a bubble, and the energy difference drives its wall outward at essentially the speed of light, rewriting the vacuum itself as it goes. Inside the bubble, the constants of nature are different. Atoms as we know them cannot hold together. Chemistry, structure, and observers are not merely destroyed, but rendered impossible. And because the wall travels at light speed, no signal can outrun it to warn you. There would be no astronomers tracking its approach, no final broadcast. One instant, the sky is ordinary. There is no next instant. Now, the honest caveats, which matter enormously. The calculated lifetime of our vacuum comes out to numbers like 10 to the power of a few hundred years, so far beyond the age of the universe that the threat is, for any practical purpose, zero. And the calculation itself leans on extrapolating known physics across enormous energy ranges, where undiscovered particles could change the verdict entirely. Metastability is a suggestion from current data, not a settled fact. But notice something eerie about this scenario through the lens of everything we've built. Vacuum decay is a quantum event, undetermined, branching. In Everett's picture, if a bubble nucleates in one branch, there are branches where it doesn't. An observer's experience, following the suicide machine's cold logic, continues wherever the sky remained ordinary. The most absolute apocalypse physics can describe is precisely the kind of death quantum immortality is built to sidestep. Which is what makes the second prognosis so much more serious. Because the second death is not a quantum coin flip. It does not branch. It happens in every branch, to every copy, on the same relentless schedule. In 1998, two teams of astronomers measuring distant exploding stars made a discovery that rewrote the future of the cosmos and won the Nobel Prize. The universe's expansion is not slowing down under gravity's pull, as nearly everyone expected. It is speeding up. Something, physicists call it dark energy, a name that mostly measures our ignorance, is pushing space apart faster with every passing era, and its dominance is growing. The consequences unfold like a slow-motion tragedy in acts. The age of star formation is already past its peak. The universe forges new stars at a small fraction of the rate it managed billions of years ago, because the raw gas is running out, and expansion is starving galaxies of fresh fuel. The stars that exist are spending down a finite inheritance. Our own sun has perhaps 5 billion good years left. The smallest, thriftiest stars, red dwarfs sipping their hydrogen, can burn for trillions. But in roughly 100 trillion years, by our best models, the last of them gutters out and the age of starlight ends permanently. What remains is a universe of remnants, white dwarfs cooling toward blackness, neutron stars and black holes, drifting through a darkness that accelerating expansion keeps emptying as galaxy after galaxy is carried beyond every horizon. Given enough time, and here the timescales become almost obscene, even the remnants fail. If protons themselves decay, as many theories predict, ordinary matter dissolves over 10 to the power of 30 plus years. And the black holes? We already know their fate. We watched Hawking derive it 2 episodes ago. They evaporate, the largest taking perhaps 10 to the power of 100 years, until at last even the deepest gravitational vaults have paid out their information and vanished. What is left afterward has a name that sounds like poetry and is actually thermodynamics. Heat death. Not heat as warmth, heat as uniformity. A universe at maximum entropy, where temperature differences have evened out, energy gradients have flattened, and nothing meaningful can happen anymore. The second law of thermodynamics, the same patient force we met in Part 1, reclaiming a body once its maintenance stopped, finishes reclaiming everything. And here is why heat death, not vacuum decay, not black holes, is the true wall at the end of our story. Recall what death turned out to be, all the way back in the first episode. Not the loss of matter, but the moment a pattern stops being able to maintain itself. That definition scales. Thinking, experiencing, being an observer. These are physical processes, a kind of computation, and computation has a strict, non-negotiable fuel requirement. Free energy, meaning energy in a usable, ordered form, flowing from hot to cold, from concentrated to dispersed. A universe at maximum entropy still contains all its energy. Conservation guarantees it, but the energy is level, like water spread across a perfectly flat plane, with no height left to drive any wheel. No gradient, no computation. No computation, no thought, no perception, no observer. It is worth knowing that physicists have genuinely tried to engineer an escape. In 1979, Freeman Dyson published a serious calculation suggesting that patient beings in a slowly cooling cosmos could think an infinite number of thoughts on a finite energy budget, slowing their clock speed forever, hibernating through the deepening cold. It was a beautiful loophole, and the 1998 discovery closed it. In a universe whose expansion accelerates, a residual haze of horizon radiation sets a floor temperature beneath which nothing can cool. And against that floor, Dyson's infinite thrift fails. As always, honesty. Dark energy's long-term behavior is measured over billions of years and extrapolated over trillions. And if it weakens or changes character, a possibility current data cannot exclude, the far future reopens. But if the universe we measure is the universe that persists, then the conclusion is stark. Quantum Immortality's engine was survivorship. Among all futures, experience flows into the branches where an observer still functions. Heat death is the point where that filter has nothing left to select. Not a bullet with a lucky branch beside it, a horizon closing on every branch at once. The tree of futures doesn't get pruned, it runs out of soil. So the promise, even at its most generous, was never immortality. It was a reprieve, unimaginably long perhaps, but bounded by thermodynamics on one end and built, at the other, on an interpretation of quantum mechanics that remains unproven. And we have been generous. For 5 episodes, we have followed this idea's logic wherever it led, granting its assumptions to see how far they reach. Now comes the reckoning. Because serious physicists, including some who fully accept Everett's branches, look at quantum immortality and say, no. Not because the universe ends, because of a flaw much closer to home, hiding in the one word this entire series has leaned on hardest: probability. And alongside it waits the objection we deliberately locked away in Part 3, the one about how people actually die. It is time to open that door. Every honest story about an extraordinary idea owes its audience one final thing: the strongest possible case against it. Not a token objection, knocked down to make the idea look invincible. The real case, made by the people best qualified to make it. So here is a fact worth sitting with. Most physicists who accept Everett's branching universe, who believe on the mathematics that other versions of you genuinely exist, still reject quantum immortality. Not out of squeamishness, and not because the universe ends someday. They reject it because of 2 objections that strike much closer to home. One hiding inside the single word this entire series has leaned on hardest, and one waiting behind the door we locked in Part 3. It is time to face both, and then to see what, if anything, is left standing. The first objection begins with something we have quietly stepped around for 6 episodes. Everett's branches are not created equal. When a quantum event splits the world, the mathematics assigns each branch a number, a weight, given by a rule discovered by Max Born in 1926. Decades before anyone dreamed of many worlds. Those weights are not decoration. They are the entire predictive content of quantum mechanics. When a laboratory says an atom has a 30% chance of decaying in the next hour, that number is a Born weight, and a century of experiments confirms it with a precision unmatched anywhere in science. Now watch what this does to the suicide machine. After 10 rounds, a branch exists where the experimenter heard 10 clicks. We established that, and nothing about it was wrong. But that branch carries a weight of roughly 1 in 1,000. After 100 rounds, 1 in a number with 30 digits. The surviving branch exists, but so does the mathematical verdict that it is, by the theory's own accounting, an almost weightless sliver of reality. And here is the question on which everything turns. What should you expect to experience? Any branch that exists, or the branches in proportion to their weight? The advocates of quantum immortality say the weights don't matter, because experience, wherever it continues, feels total. The weightless survivor feels no thinner than the original. Their critics, including physicists like David Wallace and Sean Carroll, who have spent careers defending Everett, answer that this move breaks quantum mechanics itself. If weights don't govern experience, why does every laboratory on Earth see frequencies that match them perfectly? A rational being inside the branching universe, they argue, must treat Born weights as exactly what probability has always been. And by that reckoning, sitting in the machine's chair means expecting, overwhelmingly, to die. The dispute has a name in the literature. It is part of what's called the measure problem. And you should know that it is genuinely unresolved. Not unresolved as in fringe, unresolved as in the sharpest minds in the foundations of physics, still publish opposing answers. Quantum immortality lives entirely inside that open question. That is both its shelter and its cage. The second objection needs no mathematics at all, which is what makes it so devastating. Return one last time to the machine and notice the quiet engineering miracle we granted it without argument. Death faster than perception. A perfect binary, one branch fully alive, one branch containing no observer at all. The entire survivorship argument slid through that clean gap. Experience continues where experience exists, and the alternative is literally nothing. But now, step out of the thought experiment and into the world and ask, when has death ever been like that? Real endings are not binary. They are continuums, illness that advances by degrees, injuries with 1,000 gradations, minds that dim before they go dark. And branching is merciless about continuums. For every future in which you cleanly survive some danger, the tree holds vastly more futures of partial survival, versions weakened, versions damaged, versions barely maintained. The filter we discovered in Part 3, experience flows wherever it can continue, does not select for health or youth or recovery. It selects for the barest flicker of continuing experience, because that is all the logic requires. Follow quantum immortality honestly through a real human life, and it does not promise an eternal prime. It promises that experience keeps finding branches where it hasn't quite ended yet. Even Max Tegmark, the man who sharpened the thought experiment and mapped the multiverse's levels, has made exactly this point. Dying, in reality, is almost never a single quantum coin flip, and so the machine's beautiful logic may simply fail to transfer to the world outside the laboratory. Taken literally, the idea leads somewhere far darker than immortality. That darkness is not a reason it's false, but it is a reason that no one who understands it should want it to be true. And it explains, perhaps, why physicists discuss this idea in hallways more often than in journals. And beneath both objections lies the foundation we have flagged at every step, which must be said one final time without flinching. All of it, branches, weights, survivors, assumes Everett was right. No experiment has yet distinguished many worlds from its rivals, from interpretations where the wave function physically collapses, from theories where particles ride pilot waves through a single history, from proposals in which collapse is a real process that experiments might one day catch in the act. Physicists are testing quantum mechanics with ever larger objects, pushing superposition toward the scale of the everyday. And so far, the equation has never blinked. Every test has widened the territory where the mathematics holds without collapse. That trend means something. It does not mean victory. If collapse is real, there is one history, one you, and this entire series has been a tour of an exquisite mathematical mirage. So, the reckoning. What actually survives? Strip away everything the objections can reach and look at what remains, because it is not nothing. It is, in fact, everything we verified along the way. That death, measured by every instrument physics possesses, subtracts no substance from the universe, only organization. That you are not your atoms, which have already left you many times, but a pattern written in them. that the equation governing that pattern's every particle describes, without ever collapsing, all outcomes at once, and that this is not fringe speculation, but a leading reading of the most successful theory in scientific history. That if space runs deeper than our horizon, arithmetic itself forces your pattern to recur. And that when physics built its ultimate erasure machine, a black hole, and asked whether the universe could truly delete a pattern, 30 years of war ended with the most famous scientist alive conceding that, apparently, it cannot. None of that is the 1%. That is established science and serious mainstream theory, and it will still be true tomorrow, regardless of how the interpretation war ends. The 1%, the sliver that survives the math but cannot yet be confirmed by it, is the connecting claim that because experience can only ever be found where experience continues, there is always, somewhere in the vastness, a next moment. A claim that no experiment can test from the outside, that its own probability rule testifies against, that would be terrible in ways its admirers rarely admit, and that nevertheless refuses, on pure logic, to die. Which is fitting. We began with a question that sounded like it belonged to religion. What exactly dies? 7 chapters later, look where it lives now, in decoherence timescales, in the flatness of space, in the entropy written on a black hole's skin. Whatever you conclude, that migration is the real event of this story. The oldest human question has become a physics problem. It simply hasn't become a solved one. So we end where honesty demands, not with an answer, but with the question sharpened to a point. If Everett's equation means what it says, then at every moment, including this one, the pattern that is you branches into futures beyond counting. In almost all of them, eventually, the pattern fades, and the universe, unable to forget, files it away in ink that nothing can erase. But always, somewhere, by the cold logic of experience itself, a version of you wakes up. It remembers everything you remember. It feels exactly like being you. It is watching a sky, breathing, continuing, certain as you are certain now that it is the original. Perhaps the born rule closes the door, and death is precisely what it has always appeared to be. Perhaps the universe is stranger than that. But if even one thread of this story is woven the way Everett believed, then somewhere a version of you always wakes up. Which one is you?